Hello everyone, and welcome to my channel. This is an educational channel, and we try to shed light on some great theories of everything and other information that you may not know about because it's been suppressed. And today is our 448th video that we've done on the reciprocal system of theory from Dewey B. Larson. And Mr. Larson was an engineer born in 1898, died in 1990, born in North Dakota, moved out to Portland, and I think lived the rest of his days out there. And I think around 1930, he had some epiphanies as he was just trying to work on some chemistry research. And he took them to heart. And he developed his ideas to the point where in 1959 he proposed his two fundamental postulates about how he thought that the universe operated. And then while he was doing that, he took those postulates and put them through a process of deduction, kind of an if this then that approach. And he arrived at a theoretical universe, kind of like if my two postulates are correct, this is what my universe would look like. And then he wrote some books where he compared his theoretical universe with the measured universe from the legacy scientists, the results of their laboratory and observatory experiments, and compiling them in scientific tables and so on. We're looking at one of his books called Basic Properties of Matter, and this is on chemistry. So he derives equations for many of the basic properties of matter, such as the specific heat and the melting point and the compressibility of different substances, different elements and compounds. And then he compares them to the scientific tables, and unless he's fudging the numbers, which, you know, is possible in this world of deceit, he's able to really practically recreate the scientific tables at very little expense. It took those guys, thousands of them, hundreds of thousands of them, maybe over centuries, with trillions of dollars of research to compile those tables. And Larson was able to do them with a slide rule from his living room. That's that's the power of having a theory of everything. You are able to investigate areas that you're not able to necessarily penetrate with your senses. You can do it in your head. And we are looking here at chapter 5, which is on heat. And just it kind of goes over the heat relations and the specific heat, and then kind of the melting point, the various machinations that different compounds, different substances undertake to avoid reaching that melting point. And before we get into that, let me just give you a quick once-over on the reciprocal system. The reciprocal system is also known as the universe of motion because Larson proposed motion as the fundamental of the universe. Not matter, as the ancient Greeks did all the way up until the late 19th, early 20th century, or energy, as Einstein and maybe Heisenberg would have advised, but motion. And Larson's first postulate sums it up. The second postulate is mainly axiomatic, having to do with math and geometry. But the first postulate states that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. Okay, so that's where you get the reciprocal system from, is that motion is, the world is made out of motion, and motion is the relationship between space and time. Space and time are reciprocals of one another, and you can see that in, if you look at the most basic kind of motion, speed. Speed is the car is going 15 miles per hour. 15 miles of space in 1 hour of time. Space over time. That is a relationship between space and time. That is just speed. But Larson applies that to all of our scientific phenomena and says that they are all forms of motion, and that they are all fractions, with time or space as the numerator and space or time as the denominator. Now, if you want to double the speed, you can say now the car is moving 30 miles per hour. Or equivalently, you can say now the car is moving 15 miles per half hour. You can double the space, or you can halve the time, and you get the same result because they are reciprocals of one another. So at least in speed, space and time are, in fact, reciprocals of one another. But Larson, again, extrapolates this to all the other forms, such as matter and energy and force and acceleration. And they all have their signature time-space configuration. So in Larson's system, energy is time over space. Matter is time to the 3rd power over space to the 3rd power. Pressure is time over space to the 4th power. Force is time over space to the 2nd power. And then you can kind of check your basic equations for validity. Say you've got force equals mass times acceleration. Force is time over space to the 2nd power. Mass is time to the 3rd power over space to the 3rd power. Acceleration is space over time to the 2nd power. The rock fell out the window at 32 feet per second. Space over time to the 2nd power. And then you multiply that out, and the units work out. Or if you have pressure equals force per area. Pressure is time over space to the 4th power. Force is time over space to the 2nd power, and area is space to the 2nd power. So E equals mc squared, you can do that, or any other equation. It's very useful to do it that way, and it's more useful than the MKS system because MKS has matter involved, and in this system you just convert matter into T third to the 3rd over S to the 3rd, and then you're only dealing with 2 variables instead of 3. Okay, now when Larson is making his universe out of motion, the first thing that you have to keep in mind is that motion precedes everything else. The universe is made out of motion, so you have to be able to conceive of a universe with motion without anything moving. There is motion before there is a thing moving. Motion precedes everything else. And if you can't get with that, then you can't get with the system at all. You might as well just give up right there. You have to be able to conceive of that before you can embark on studying the universe of motion. Or you can just accept it, or you can concede it, for further verification. But that's conceptual step that you have to be able to take. Another is that, for 3,000 years, we've thought of the space and time as being the background setting of the universe, that we are, that space and time are basically the stage upon which we go through our paces, our daily drama, and that, we are moving through a still frame of space, and things are unfolding in time. But in Larson's universe, space and time are the contents of the universe, not the container, but the contents. And so those are kind of conceptual hurdles that need to be jumped over before you can get into the reciprocal system. Now, when Larson is referring to motion, he's also referring to what you would call a scalar motion, which is a more generalized kind of motion that's not terribly recognized by scientists, although they do concede its existence because they have to, because it does exist. A scalar motion is a motion that has a magnitude, but it has no specific direction. You can envision a scalar motion if you take a balloon and you put dots on it. You blow up the balloon, all of the dots will be moving away from each other. Every dot will be moving away from every other dot. And in fact, the locations between the dots will also be moving away from one another. And that is an outward scalar motion. And Larson refers to that as the progression. Now, if you suck in the balloon, all of the dots will be moving toward each other, and that is what Larson calls gravitation. And when they do move toward each other or away from each other, it appears as if there is a force connecting those different dots, that there's a force field or some kind of force of repulsion and or attraction or attraction that is pulling those things together. But that's not the case. Each one of the dots is actually pursuing its own course, moving toward every other dot. But if you decide arbitrarily that you're going to pick one of the dots, and that's going to be your reference point, and you're going to say, this dot is motionless, then you can start measuring the directions, and you can attribute force fields to those other dots. They're all attracted by your stationary dot, and that's really what Larson calls the spatial and temporal reference points. Okay, so if you have the spatial reference point, this is basically what we normally perceive of in the universe, in our environment of the universe. 3 dimensions of space, x, y, z coordinates in a still frame, and clock time. The clock is still moving in a scalar manner, but the space is vectorial, 3 dimensions of vectorial motion. Moving, time is always getting later and later and later and later in a scalar manner in no specific direction. So, and then reciprocal to that would be the temporal reference system, where we have 3 dimensions of time in a still frame, and space is still scalar. That would be if we abstracted something in time, or if we took that reference point in time and said, we're stopping this in time, and now we're making the measurements in time. That we would only be able to do in a different environment of the universe. Okay, now also there's this scalar aspect. Now, when you have those 3 dimensions of space, that's only 1 dimension of motion. Okay, you have 3 dimensions of space, 3 dimensions of time, but you also have 3 dimensions of motion. It takes 3 dimensions of space or time just to describe 1 dimension of scalar motion. So each one of those would represent one, the scalar and temporal reference system, which would each occupy one scalar dimension of motion. And then you also have the discrete unit postulate. That is that everything is quantized. Everything comes in units. You don't have a third of something or 0.24 parts of something. You either have a whole unit or you don't have anything. You need to have a whole unit of space to have a unit of space, a whole unit of time, and a whole unit of motion. 1 unit of space in 1 unit of time is a unit of motion. If you have that 1 unit of space in 1 unit of time, Larson calls that unit speed. Space over time is speed. Unit speed is also known as the speed of light. So the speed of light is 1 unit of space in 1 unit of time, and that is the progression. The progression is this outward movement, similar to the movement of an expanding balloon, the dots on an expanding balloon. And it is at 1 unit of space per 1 unit of time, or the speed of light. Larson refers to this as the progression of the natural reference system. This also means that half of, so Larson also refers to this as the null point or the 0 point, the neutral point. So this is the neutral point, meaning that half the universe is actually moving faster than the speed of light and half is moving slower. Larson refers to these as the cosmic sector and the material sector, respectively. In the material sector, we have, this is where we reside in the slow region, and we observe coordinate space and clock time. But if we were in the cosmic sector and we were moving faster than the speed of light, we would observe coordinate time and clock space. So when we cross that speed of light boundary, we move from this spatial reference system to the temporal reference system. The roles of space and time reverse. Now, within the material sector and within the cosmic sector, there are also many boundaries, many regions, where you don't have a full unit of space in the material sector. Atoms and particles can interact in areas less than 1 unit of space, which is approximately 2 millionths of an inch. And if they do, that occurrence does not happen in space. It happens in time. And because there is no space, because you don't have a full unit. And if it's not space, it's time, because the universe is made out of space and time only. And so Larson calls that the time region. That's the region of interaction of atoms and molecules. And when you cross that boundary, that unit space boundary, the rules invert again, and now the progression is moving inward in space, really outward in time. But we see it as inward in space. But there is no space. So we're not really seeing what's happening, but we are anchored to the spatial reference system. And so we only see space. And so we see it as an inward in space. And then gravitation is outward in space in the time region. So the relations reverse there. And the same is true in the cosmic sector, except there you have cosmic atoms and cosmic molecules, and you have the progression going now is inward in time, and gravitation is outward in time. Okay, now these are relevant here when we're talking about heat in this chapter of Larson's Basic Properties of Matter. But there's a lot of other details involved, and you may not be able to follow this, especially since the chapter is almost over. But we're going to try to read the rest of this chapter, and I will try to tie up any loose ends, but there's probably going to be loose ends on every sentence. But I like to read this into the record so that if somebody is really studious that they can pick this up. You have to dig, and it's a detective job. Larson did a great job of putting this down, but he's just one person, and so he was set with a gargantuan task, and he did the best he could for the resources and the manpower that he had. And he, he uses a lot of terms that you might not understand, but but you will be able to pick up a few things. And I think it's all very profound, but the important part is that it's an interconnected system. It's a system of theory. So what you can pick up about temperature or about anything having to do with chemistry, it also applies in other fields. This is unlike legacy science, where you might go to graduate school or medical school or whatever for years and study a subject, but you will never learn anything else about any other subject. But what you learn in Larson's system is applicable to every subject. So let's listen to a little bit of Larson on chemistry here. Okay, these values, he just showed some values of the specific heat. The specific heat is the amount of heat that you have to add to something in order to increase the temperature by a specific amount. It's basically the, if you take the derivative of the, it's basically the rate of temperature increase. These values and the maximum specific heats previously calculated for the successive curves enable us to determine the relative temperatures of the various transition points. These transition points are the points that the atoms or molecules use to avoid crossing that melting point. Because, as Larson says in his second postulate, the universe conforms to the relations of basic commutative mathematics. And so he uses a lot of probability to determine what can occur. And generally, the lower the temperature, the more probable it's going to be. Also, the lower the number, the more probable. And so the elements will do everything that they can to avoid crossing into the liquid as opposed to the solid state. And so they undergo various transitions, which have to do with the structure of matter, which I get into in a lot of episodes, but not today. We're going to try to keep moving here. In the rotation 3 curve, for example, the temperatures of the first and second transition points are proportional to the differences between their respective specific heats and the 3.89 initial level of the rotation 2 segment of the curve, as both of these points lie on this line. The relative temperatures of any other pair of points located on the same straight line section of any of the curves can be determined in a similar manner. So he's basically saying that all these curves, he's basically establishing a specific heat curve, and it has inflection points, because whenever the atom or molecule takes hits a transition where it goes through the transition to avoid crossing this melting point line, the curve takes an inflection and it goes on to a different angle. The total curve is basically a connection of a bunch of line segments. But if you extend the curves all the way back to the 0 ordinate, then they all meet at the same point. And so basically all of the atoms are on the same set of curves. So this temperature system is basically universal. The relative temperatures of any other pair of points located on the same straight line section of any of the curves can be determined in a similar manner. By this means, the following relative temperatures have been calculated based on the temperature of the first transition point as unity. And so he talks about the various vibrating units, relative temperature, and so I'm not totally familiar with these numbers, but at transition 1 or unit 1, the relative temperature is 1 exactly, and the end point is 1.8. The second curve, or the second line, begins at 2.556 and goes to 4.56 at the end point. And the third curve starts at 3.086 and goes to 9.32. And the fourth curve starts at 3.391 and goes all the way up to 17.67. And these are the endpoints. And so depending on what kind of atom or what kind of particle you have and how many kind of resources it has available to change, to make transitions, these are going to be the endpoints. And so certain of the elements or molecules, compounds, have higher or lower melting points, but they all are going to fall on one or another of these curves, depending on how many rotational aspects they have in their atoms. Now, an atom is basically based on rotations. They are rotations of that original progression. The outward movement of the balloon is the source. But in order to harness that source, it has to be rotated back in 3 dimensions. And so Larson uses a 3-number system in his periodic table. Every element contains 3 numbers. One is the primary 2-dimensional rotation, the next is the secondary 2-dimensional rotation, and the third is the oppositely directed 1-dimensional rotation, which is optional and can be negative. And so he uses those values in order to kind of ascertain these curves. And the more of those rotational values that you have, the more flexibility you have in order to overcome the increase in heat and stay inside the solid state. The curves of figures 3 and 4 portray what may be called the regular specific heat patterns of the elements. These are subject to modifications in certain cases. For instance, all of the electronegative elements, those that are basically on the right side of the periodic table, with displacements below 7, less than 7 units away from the noble gases. Thus are their valence. Thus far studied substitute an initial level of a negative 0.66 or negative 2/3 for the normal 1.32. It's actually a little bit less than those 2/3 because you're multiplying it by a number that is just under 2. Okay, another common deviation from the regular pattern involves a change in the temperature scale of the curve at one of the transition points, usually the first. For reasons that will be developed later, the change is normally downward. Inasmuch as the initial level of each segment of the curve remains the same, the change in the temperature scale results in an increase in the slope of the higher curve segment. The actual intersection of the 2 curve segments involved then takes place at a level above the normal transition point. These are some deviations of a different nature in the upper portions of the curves where the temperatures are approaching the melting points. These will not be given any consideration at this time because they are connected with the transition to the liquid state and can be more conveniently examined in connection with the discussion of liquid properties. As mentioned earlier, the quantity with which this and the next two chapters are primarily concerned is the specific heat at zero external pressure. In chapter 6, the next chapter, the calculated values of this quantity will be compared with the measured values of the specific heat at constant pressure, as the differences between the specific heat at zero pressure and that at pressures of observation is negligible. And that is because the pressures of observation are very, very low on the natural scale standard that Larson uses, where the unit of pressure is something on the order of 15 million atmospheres. Okay, most conventional theory, so then the pressure that we normally encounter in the environment is basically negligible, or it's basically zero. Unless you were, doing extremely accurate experimenting, but these are just, initial forays into the subject. So most conventional theory deals with this specific heat at constant volume rather than at constant pressure. But our analysis indicates that the measurement under constant pressure corresponds to the fundamental quantity. And I don't understand that at all. But again, it's detective work. So if you don't understand something, you don't get discouraged. You just chalk it up in your mind and you move on. And a lot of times Larson will clear up the confusion pretty soon thereafter. Sometimes not. Sometimes you might have to read it in a different book of his. That's what makes this so hard, and I guess that's kind of what I'm trying to do, not with these videos, because with these videos I'm just trying to introduce people to the system. But my work, at least at this point, at least part of my work, is to try to take Larson's work and put it on a silver platter for people, basically like putting together a textbook or something like that where all of the key points are there, and you don't have to, every time you see a term, you don't have to look it up. It's right there and stuff like that. So anyway, good things are in store for the reciprocal system. Thanks for tuning in.